Okay, guys, are you able to see the slides? Are you able to see the slide, guys?
Yes, sir.
Okay, thank you very much. Today we're going to start section 4, which is the block diagram reduction techniques. So this is also one of the important chapter that we are going to do in control system. I would like you to give me attention. This chapter is not difficult. Is I can even say it's the easiest one, but you need just to understand how the techniques works, so you might be able to solve anything. Please, can you switch off your microphone? You're already in class. So let's do now. As an introduction, we are going to start by the definition. I think the word block diagram is not like new to you because you have already heard it. We talk about the block diagram in the first section in introduction of control system, even if what we call the architecture of a control system, it was just a block diagram representation of a control system. So as a definition, we can just say a block diagram is a short-hand graphical representation of a physical system illustrating the functional relationship among its components, or a block diagram is a short pictorial representation of the cause and effect relationship of the system. So I think the definition is just very clear. So the block diagram is just allowing us to represent to have a graphical representation or a schematic of a physical system, and a system which many components we can just represent it and show how the components are linked together. So as we had that example, the one we saw on the first section when we had the actuator, controller. So those are different components that we had to put together to do a graphical representation of it. That's in simple way that we call the block diagram. So as you can see on your screen, we are going to show just the simple form of the block diagram. The simple way of representing a block diagram is what you can see here. Just a way you represent your input and the output and so on the system, which can be represented by a transfer function, as you know, or any mathematical relation in or in mathematical model of a system. So if you can see here, we have if you see here, we have the input x of t and the output y of t. So this is a representation in a time domain, and this is the representation in a frequency domain. And g of s, you know, all of you, that is the transfer function. X of s is the input and y of s the output. So now we want to see what are the components of a block diagram, how the block diagram is made. So the block diagram is, to get a block diagram, we need certain components, we need certain things to put them together so we can have the block diagram. As you can see, I told you that we are busy talking about the linear time invariant system. So now we're gonna see how we can make a block diagram of a linear time invariant system. So the component of a block diagram, we can just notice 4 components of the block diagram. The first component is the signals which can be our outputs and our inputs, that we call the signals of a block diagram. And beside the signal, we have the system itself, which is represented by a block, as a block where we can have a transfer function or a mathematical relation inside of it. So it can be anything that can be represented, a block that is representing our system. And we have the summing junction. The summing junction, I think you have seen something like that before. I explained it in the introduction to control system. So maybe there is this last element, which is the pick off or take off points. I think it's quite new for you, but we are going to see what is it exactly. So as you can see here, we are representing all the 4 components of a block diagram. The first one is what we call the signals. We have RS, which is the input, C of S, which is the output. That is the signal. We have the system by the transfer function G of S, and we can see the signal are represented by the arrows. So that show the way it's going in or it's going out. And then we have the summing junction. So the summing junction in easy way is just a point which receiving many signal as input signal and send them out as a sum of many signals. So there can be many signal getting in the summing point, and at the output, the sum of all the signals. So we can have as many as we can, but the output of the summing point is given the sum of the signal. If you can see here, there's something that you can notice. You can see next to RS, there is a positive sign. Next to RS2, there is a positive sign, but to R of S3, there is a negative sign. So that means when there is a negative sign, it means that that signal must be subtracted from the signal. If the positive, it must be added to the total signal or the output. So the peak off point is or takeoff point is like I can say in a simple way, like is a splitter of signal. So when we have like our input signal, we want to split it in many block. We want to send it in many block or in many feed forward or feedback. We use the peak off point. So we can distribute here. We can distribute the input signal in many other block diagrams. So that is the peak off point is used for. So now let's go and see. This is what I've just explained to you, how we can distribute more signal to one signal to many different output or several points. So I want just now you to see this simple example that we are going to do here. They say consider the following equation in which x1, x2, x3 are variables, and a1, a2 are general coefficient of mathematical operators. So as you can see here, they say x1 and x2, x3, they are variables, and a general coefficient of mathematical operators. So just by the way they define this value, you can be able to understand what can be your input, what can be your output, and what can be represented as the block diagram. If you can see here, they say a1, they are mathematical operators. So that just means that they're gonna be part of our system. So as I told you that the system or the block diagram, we can have some mathematical model inside, or you can have any transfer function. So in an easy way, when we want to write this signal, so we can just say, we can make it simple and say our signal gonna be like this one here. We have a times 1. So we can just say, okay, our inputs, let's say the inputs here is going to be x1, this is the input, and we have our block which contain the mathematical operator, which we can call a1, which is called a1. Let's say a1. Okay, we have a1 here. Here we have a1, and the output, as you know all, that the output is equal to what? The product of the input and the transfer function. So the output will be a 1 times x1. So this is in another way how we can represent this A1 in terms of block diagram. So we have the input, which is our variable, and we have the operator, which is the system, and we have the output. Same, we can do the same thing for A2. Let's say for A2, you can say we have x2, and we have the arrow, which can be represented by, let's say this one. Let's use this one. Okay. And here we have A2 x2, and there we have what we call A2. So you have seen that we have represented these two signals in terms of block diagram, knowing that this one is not connected to any operators, mathematical operators. So it's alone. We can just write there's 5. You can write it like 5, like this. Then say okay. So as you can see, this one, it's the output is x3. X3, our output is the sum of this one, and that one. From that we have seen before, we have seen some components. We know that there is one component that we call a summing junction. So it's taking many signals and put them together, adding them together. So we can just understand that there must be somewhere here a summing junction, which gonna give us now. And this one, because it's minus, we can put it in the summing junction the way it is. Let's put like something like this one, and have it like this, and we can have it like that. Okay, so this is gonna be like minus. Then this signal can go there. This one also can go there. Now put the arrow there. Because they are positive, we're gonna put plus plus, and our x3 must be somewhere there. So this is something very, very easy to understand. So I'll just try to explain to you how these things works. Let's see now what we can do from here. Okay, let's see what is happening here. So this is in short how you can solve this kind of signal. So you need just to understand the concept and say, okay, this is what, then you can be able to draw your block diagram following this one. I did it because I didn't draw it properly, but I think in the slide that I'm going to share, and probably even here, there is already the slide that you can see them in the slides. And okay, let's do this. Okay, this is how our signal is going to look like. So now you can see this one. This one is not representing the same way I represented, because they have already represented for you this A times 2 as they took it from the output. But if you want to start from the input, you will do the way I did it. So now you have already A1 here and A2 there that are represented. So let's now see what's going to follow after this one. So let's see. So, okay. So this is now showing what I was expecting. That, sorry, switch off your mic. Okay. Please. Please. Can you switch off your mic? Sorry, guys, you are disturbing us. Guys, you are disturbing us, please. Okay. as I was saying, that you can see here, they show you already the response there, but this is how you can represent this signal. That's why I draw it, putting the block diagram. So X, and we have A there, that's going to give you X times 1. So now there is another example here. So this is how you can solve it already. The first is the same example that I gave to you. So you can represent it in this way, the way I did it for you. So now there is I think this is another example which they show you as when you have n signal, how you can represent it. It's exactly what I've shown you before. So this is not new for you. Then there is these two problem. I think you can try. I think you can try to solve them, and yeah, you can try to solve them. Maybe I will see. I will add some question. You can do it as an assignment that you can submit on Monday in class, in the lab on Monday in the morning. But I will confirm with you tomorrow. I might probably add. I might probably add other question from the previous section, so you can submit as an assignment. I'm gonna see how I'm gonna do with it. Okay. Thank you. So this one you can solve it also easy, the same way. I think I can explain. So you can take this one as a one signal or one block, and this one can be also one block, and that one too, one block, and this one also one block, and so on. You can draw now the summing point and get the signal. So now let's see the topology of the block diagram. So this is also very important. You know, block diagram is just working with the concept, knowing the topology, knowing how you can connect them. You can see that it's something very, very, very easy. So we have different topology. The first one we're going to see is what we call the cascades. Cascades is like putting in series, as you know, in series. So how we can solve block diagram in series when you have like 3, 4, 5, or 2 block diagram in series. That's mean one block after another one. How we can solve those blocks. So the first topology that we are going to use in control system is the cascade. So and it's one of the elements that can help you to reduce a complex block diagram system. So let's see how it works. So this is now they are showing an example. They say when we have a cascade block diagram like we have here, we have this is the input, this is the output from the first block diagram, and this is the total output. They say, okay, when you have this kind of block diagram, to solve them, it's easy. So the equivalent block diagram of these two will be just the multiplication of, we multiply G1 times G2, then it's gonna give you one block diagram, then you keep your input signal. So this one is multiplying this one. So this one times this one. So when you do when you do the cascade block diagram, you know that it's a multiplication of block diagram. So this is really something very easy. It's not really complex for everyone. You all know how you can solve a series when two block diagram are in cascade or they are in series. You know how you can solve them. So now they say multiplying them is like when you have here from any number, when they are putting, they can be even 10 block diagram in series. You have just to multiply them. So let's see another example. So this is just a simple way to understand what is happening. So we have this is the input RS, and we have this is the first block diagram, and this is the second block diagram, the third block diagram. So if they ask you to find the equivalent transfer function of this block diagram, so you know that because they are in series, the equivalent transfer function must be the multiplication of G1 of S times G2 of S times this one times G3 of S. So this will be the equivalent transfer function of your block diagram. So here they're just showing us in short, calling this signal, they say this one is like X2. So X2, they just consider the output of this first block diagram. We know that all of us that the output is equal to the input times the block diagram. That's why they write here G1 of S times this one. Then for the output of the first block diagram will be the input of the second block diagram. So we know that this is the output. Then to find the output of this second block diagram, it's gonna be, now you do this transfer function times the input, which is G of S, R of S, then that's why they got this one. Then for the third block diagram, the input will be the output that we got from the second block diagram, or we can call it X1, which is G of 2 times G1 times R of S. And the output now will be this input times G3 of S, and we got this, that will be the total output of the block diagram. So when we want just to consider the transfer function, the transfer function will be the multiplication of only this 3 block diagram. That will be our equivalent transfer function. Don't confuse the equivalent transfer function and the final output. On the final output, there must be the presence of the input signal. That's what we can see here. We solve first the transfer function, which gives us a G1, G2, and G3 times RS. So this is now the transfer function, and we consider this is our input and output. When they ask you to find the output, you're going to just use this RS times this one. When they ask you to find the equivalent transfer function, you can even just say, okay, let's call this one, you can say it is like G. You can say G is equal to G of S. This is the equivalent transfer function, which is going to be equal to the multiplication of all these transfer functions. So you can see that we are talking about the cascade subsystem and the equivalent transfer function. So yeah, this is the equivalent transfer function that is shown in this last formula here. So now there is another concept that can be used in that can be used here. The other concept is the parallel form. So the parallel form, after we finish with the series form, now we can talk about the parallel form, which is the parallel form. As you know already what is the parallel form is. But remember, I want to show something very important. For you to say that the block diagram is in parallel, you need to follow the direction of the arrows. If all the arrows are going in the same direction, like this one and that one, you can say these two block diagram are in parallel. If those arrows were going in the opposite direction, this was supposed to be something else. It is not a parallel block diagram. So you should be careful. So look for the direction of the arrows, so that can help determine whether it is the parallel or something else. So for the parallel, it's also easy to understand. The parallel is just to do the sum of the block diagram. When two block diagrams are in parallel, what you need to do is just to do the sum. You do G1 of S plus G2 of S. That's all. That's gonna be your equivalent block diagram. So this is just show us that we have, as you can see here, we have what we call the takeoff points here. We have one signal going in G1, G2, and G3. And those signals are giving us our output signal. Don't mind first this notation here. Let's just use this one, this line here. We go there, and this one we go there, and this one we go there. So you can see that the signal from G1, from G2, from G2, all of them, they are going in the summing point. As I told you, the summing point, there is different sign. That sign will determine whether it's subtracting the signal or it's adding the signal. So the equivalent block diagram will be this one, G1 plus minus, depending on the sign of the signal or the sign of the block diagram, will be G1 plus G2 plus G3, or G1 minus G2 minus G3. And now here they are just showing us what I told you is the output signal, which is equal to the input signal RS times the block diagram. But what is matter now is us to know how we can find the equivalent block diagram when the block diagram they are connected in parallel. So you just have to do the sum of the block diagram, you add them together, so you get the equivalent block diagram as it's shown here. So this is the equivalent block diagram, and we have our when we have our input signal and our output signal with our transfer function, which is inside there. So the equivalent transfer function, as you know, for the parallel will be in this form. This plus minus is just showing that it depends on the sign. Okay. So now I want to show you this. That's why I was telling it's very important to be able to identify whether it's a parallel or not. Now we are going to see a feedback form. Remember, this control we are doing. It's very important because we are dealing with the feedback control. So the closed loop control. So the feedback, in another term, is a closed loop. So you know already what is the feedback. We have seen it in first session. So it means that when there is a signal, it's the return to is the output that is going back to the input, so it can go to the comparator, whatever, and the controller, and you can have the actuating signal that's gonna go again in the plant. So now we are going to analyze the feedback. You know, for the first one, if you can see, just the drawing look a little bit similar to the first one, but the difference is here the signs of arrows are different, and you can even see that it doesn't matter about the, you can see when the summing point is also before the signal, so it's bringing back the signal to the input. So when the sign here is negative, we talk about the negative feedback, and when it's positive, we talk about the positive feedback according to the sign. Then how can we now write the feedback of the feedback form when we have two block diagram connected in a feedback way, in feedback topology? How can we find now? Can we find our output signal? So this is what, or the equivalent transfer function. This is what we are going to see now. So remember here, there is something that I want to talk also on this point here. If you see this first block diagram, we have our input, we have input transistor, we have the ES. This ES is an error, or in another way, it can be called the actuating signal. So that means this is the signal we are going now to insert in our system, the signal that got already a feedback of the output. So we call it the error because this signal it's comparing and doing the summation of the output and the input. So in a simple way, this ES is equal to RS minus CS. So it's the input minus the output. So we got the feedback, the output, the error signal, which, or the actuating signal, which is going again to give a certain functionality or a certain action to our plants. This one is going to equal to ES is RS minus C of S. So this is signal. So remember, this one is going to be very important when we are going to talk about the steady state error. So after this this chapter, we are going to deal with this steady state error, the error signal, how it is. So now, when they give you this kind of block diagram, You can see now they even show us what we saw in class: controller, plant, feedback, output, transistor, which are like can be sensors, whatever. So now, how can you now find the equivalent transfer function, or you can find the output signal? Please switch off your microphone, your music.
ايوه.
Please. Please. Okay, good. So now we have our feedback. Sometimes they can ask you to write it in the canonical form. So we'll see what is the canonical form of a control system. Like this one can be called a canonical form of a control system. It means that when we have a system with only one block that is representing the transfer function and one block that represented the feedback. So the feedback is represented by H of S and the transfer function by G of S. So this is a canonical form of a block diagram. So now, how are we finding the equivalent block diagram? The first of all, we can see that in this problem we have let's first forget about this input transducer. Let's start from here. We can start our problem from here. So the other thing, I think you will understand why I said by here, because we will see other operation later. So now we have this block diagram, controller plus plane. So we know that they are in cascade. We can first reduce these two here. So we can have one block which is made with the controller and the plane together, that can be reduced. And then the second one, we're gonna have the feedback and the output transducer. So they can also give us one block. So from this, now we can have two block and our input signal there and our output signal. So this one become one block and this one also become one block. So we still have our actuating signal. Then the output of this system is equal to, as you can see, it's G of S, which is our transfer function over 1 plus minus, or plus minus, it depends on the sign that we have on the comparator or the summing points. So this is gonna be 1 plus GS HS, and this is how we can represent this the transfer function of this kind of system. So this is how you can solve when they give you a system with a feedback. This is the way you can find your transfer function. The transfer function is equal to this one. So, and they even give you the equivalent transfer function of this system. So now we want to see certain parameters that define certain parameters that define the feedback system, because it's quite important. So the first thing that we're gonna see is what we call the characteristic equation. Characteristic equation. So as we all know that the transfer function is the ratio or the relationship of the outputs over the input. So this is how we can call, we can write the transfer function in this term: C of S over R of S is equal to G for the feedback system. Then they said in the feedback system, the denominator of the transfer function is called the characteristic equation. So it's called the characteristic equation. Remember, as we saw it in time response, the characteristic equation, which is the denominator of a second order, whatever. So this is also called the characteristic equation, the denominator of the transfer function. So wherever they ask you to find the characteristic equation of a block diagram or feedback, you need to find, when they give you a block diagram, they say find the characteristic equation. First of all, you need to know that you need to find the equivalent transfer function of the feedback system. Then after that, you can be able now to write your characteristic equation, which is the denominator of the transfer function of the feedback. So now there is certain things that we can learn together. As I told you, this is what we call the canonical form of a control system. So a canonical form of a feedback control system. It means that we have an input and we have the transfer function, then we have also a feedback transfer function. So now let us give us a new, let's give to ourselves a new way of a new concept that we're gonna use in block diagram. When we have this block diagram on top, we can now call it forward transfer function. So this becomes the forward transfer function because there is a feedback. Down we will have the feedback transfer function. So we have two transfer function here for the forward one and for the feedback one. So just put it in your mind. Unless there is some exception, in most of cases, as I told you, the transfer function is represented by G of S. But now you can also see that the feedback transfer function is represented by H. So this is what you will see it in many books, is how they write. When you see H, know that is a feedback. But it depends also, someone they can call it different, but this is a general representation of the forward transfer function and the feedback transfer function. So they give us some simple definition.
Can you start afresh, please? I cannot hear you.
Sorry. Okay. Come again.
Sir,
Yes.
sir,
Yes.
can you start afresh everything?
Why? Hello, why?
I'm lost. I didn't hear anything. Can you start at the start?
Why didn't you hear anything? Why didn't you hear anything? You don't understand or didn't hear? You had a problem.
Sir, I didn't understand.
You didn't understand where? From which part? Please.
From the start, sir.
Are you sure you are at the beginning of the class? Hello?
I'll catch up later.
Okay, so we will follow the video, then we will come back again in class when we're going to be doing tutorials.
All right, sir. Can you post the video on Blackboard?
Yeah. I'll try to do it during the weekend.
All right, sir.
Okay. So we can now move forward. Okay. Okay. Is there any question or any problem? Okay. So okay, let's move now. Okay, so this is what I was saying, that guys, hold on. I want again to restart this, to share this. Okay. 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 Are you guys able to see the screen now?
Yes.
Okay. So okay, here we are. Then as I was saying that in general way we have this simple definition, and when it's G of S, it's called the loop transfer function or open loop transfer function. C over R is a closed loop transfer function. So that means the output over the input is a closed loop transfer function, which can be written like this one. And there's a actuating signal ratio, which is E over R. It's this one. So that means when we consider things from the error signal, we can write our transfer function in this way. That's going to be our output. I think, don't mind this formula. We will be back to it when we see the steady state error. That's going to help you. And also the primary feedback. This is just some definitions. So now from here, there is a question. I think that we can also try to solve this. Say from this one, find the open loop transfer function, the feed forward transfer function. What is the control ratio? What is the feedback ratio? The error ratio, closed loop transfer function, and the characteristic equation. So you can also find the closed loop poles and zero if k is equal to 10. Okay, are we together? Please. There is definition of all these elements here, and they are also after these pages. Then they give you this question. They say from this now, you need to find the open loop transfer function. What is the open loop transfer function? What is the feed forward transfer function on this one? What is the control ratio? What is the feedback ratio? What is the error ratio? What is the closed loop transfer function? And the characteristic equation of this question. I think it's easy. You can try to find it. Anyway, we're gonna do it again back in class. Okay. So now they have given you the answers and say the open loop transfer function is given by B over S GS. This is what we, if we go back to this page, they say the open loop is this one, G times H. So exactly this is what times H. So we can go from this one, you know that G is this one and H is this one. So you can do G times H, you find your open loop transfer function. And you go to the feed forward. You know the feed forward is given by C of S over E of S. So you also be able to find what is your E of S, and you know that it's gonna be equal to G. So it's easy also. The control ratio, which is the our transfer function of the feedback, the output over the input. So you can also replace at the place of J of G, you put G there, and then you put H there. You can calculate. Use this. This is the value that we are going to use in this one. So you can solve it and get the control ratio. So you have the formula. These are the formula to find the feedback ratio, the error, and you just have to replace what is H here, what is J there, and solve it, and also the characteristic equation that we are going to find after you solve this system. So this one, we're going also to add it to your assignment that you're gonna bring on Monday. Okay, so let's now move. This we have already seen it before, just showing that the characteristic equation. Talk about it that before. Then I want to talk also about this. Is quite interesting. Is what we call the unit feedback. What is the unit feedback? So the unit feedback is a feedback system, but where there is no transfer function in the output. So the transfer function in the output is equal to 1. So our H is equal to 1. So we call it unit feedback system where the transfer function is equal to 1. Then the example here, down here, they give us a feedback system where we have H as a feedback. Then they ask us to convert this one in a unit feedback system. So this is the transformation that you can do to get this one in unit feedback system. So this is part of the transformation that we are going to see later when we need to do transformation of the transfer function. So let me just see what is happening here. Then I think Ishaile for today, because this one, I think we still have time, eh? Yeah, we still have time. Let me check the time.
No, we don't have time.
Yeah, it's up to 7. Yeah.
I'll say Shail.
Ishaile, where?
Task to attend.
Yes, sir.
No, it's not Shile yet.
Eshayile sevela sizwa.
No, it's not Shile yet. Sorry, let me just show you something here. Okay, so you have the unit feedback. Then I want us to give you a quick techniques that we can use to reduce the block diagram. So we have already seen the first one, which was the cascades. So first, when you have a block diagram, the first thing you need to look at is the cascade. How you can reduce the cascades. We know already that is to make a multiply this transfer function, then you get your equivalent block diagram. So the second one is now to combine the parallel one. If you have a parallel, how you can solve the parallel, we know already how to solve the parallel. Then the third one is now to, so this, sorry, sorry,
We can't see the slides.
you cannot see the
So
slide.
you cannot see the board.
Yes.
Okay, sorry for that. Sorry, let me try to go back and show you the slides. Okay. Yeah. Oh, so I put the board there. Okay. Now you can see the slide, eh?
No.
Are you sure?
Yes.
Yeah, now they are back. So
Yes.
let me go back. So now we are going to see the techniques to reduce the block diagram.
No.
So when they give you the block diagram, you need at least to have these techniques in mind to be able to reduce a block diagram. The first things you need to look at is the cascades. Because the cascades are easy to reduce, when you see in the block diagram there is a cascade, you need to be able to say, okay, let me first reduce the cascades. You know that the cascade is just to do the sum of the transfer function, then you have reduced it. Even even if there are many one, you can just do the same way. So the second thing is you to look for the parallel and to say, okay, how many parallel do I have in my system? So after you find the parallel, you can reduce them in this way. So you can see the parallel is giving you the sum of the transfer function. Then after that one, but all these techniques here, you just I think you don't have to memorize them. You will be using the tables to see which transformation is giving you which one. Maybe by using them most of the time, you can just you can just have some on your memory. But in like in class, we're gonna give you some what you need for that one here in control 2. So this is how you can move a summing point. They say when you have a summing point here and you want to move it to another place, this is how you can move it. So you add another one. So that one, if you put it back, it's gonna subtract. It's gonna give you the same thing here. So these are simple transformation. When you have to move it beyond, moving the summing point ahead. This is how you can move them ahead. So moving the pick off points beyond the block. This is what you were supposed to do. Moving the pick off point ahead of the block. This is what we're supposed to do. And this is when you want to eliminate the feedback. You know already what to do. You have seen it before. When you want to eliminate now the unit feedback, this is how your function is gonna look. And when we want to swap, you swap with the neighborhood summing point. You want to swap the summing point. This is how you can do it. And this is the transformation, the theorem that's are used for transformation of the block diagram. So it's really a big table. So that's why I say you cannot memorize this table. So we can just give you what you need. Like this one is giving us how you can change the feedback to the unit feedback. Here is the cascades. This one is when you use the parallel. This one is the parallel. How we can use the parallel. So this is what is happening when you use the parallel. And this is the feedback loop removing. So you can see this is the table here. Then, just in short, what they wanted to tell us is they say the block diagram got a certain techniques to reduce them. So those techniques can be in a term of steps. The first steps is to be able to combine all the cascade block using the transformation that are in the table. The second step is to combine all the parallel using the transformation that we have seen before. The third one, now you have to go to the feedback loop using transformation. And the fourth one is to shift the summing point if it needs it, if it's necessary. But it's not like in all the block diagram you have to follow these 4 steps. There are other block diagram you have to maybe just step 1 and 2 and that's all. Or you can do 3, 1, 2, and 3. That's all. So it depends on what they ask you as a question in the problem of reduction of the block diagram. And then after you finish the step 5 to 4, you can find the canonical form. Most of the time when they ask you to reduce, they ask you to get the canonical form. Unless if they ask you to find the equivalent transfer function, then you can do everything. So this is in short how you can reduce the block diagram. Let me just do with you this quickly this example. Then after this example, we are going to stop by here and continue, I think, Wednesday, because Monday we have practical. And I want also to tell the evening class that from this coming Monday, we will have only one class evening practical. So that will be from 7 to 8:30. So the 4 o'clock, because we are having problem with we are clutching with people, so it's cancelled. So we'll be having all the night one, the later ones for the 7 o'clock to 8:30. So now, please guys, listen. This is very easy for us, and you can see that there's nothing that is really difficult for us to do here. So they're asking us to reduce the block diagram to the canonical form. First things, let's go back. They say the first things you need to do is to combine all the cascades. How many cascades do we have here? We can see the cascades. We only have G1 and G4, they are in series. So we can combine this G1 and G4. That can give us now a block which is gonna be block diagram where G1 times G4. Okay. So we combine these 2 block diagram. It gives us 1 block diagram. So instead of having this one, we'll have this. This is they even show you here. We'll have this one. So then they say the second thing that we can do here is to combine also the parallel. How many parallel do we have here? You can see the parallel we have here is G3 and G2. So this one also we can have the equivalent block diagram, which is going to be G1, G3 plus G2. Okay, so this is our second block diagram. So that means we will have here 1 block diagram and there also 1 block diagram. And this part here will remain now. This one will be, sorry, let me try this line here. So now our block diagram will be divided in, so we have 1 block there, we have one system here with transfer function with G1 plus D1 and G1 times 4, sorry, this is G3 times G2 gonna be here on this place here, and here we'll also have one block or one system G1, G4. So this one gonna give us a feedback. But because of the presence of these points here, this one cannot be in series with that one. Unless we remove this feedback, then they can be in series. So let's now see how our block diagram is going to look like. So we will have a block diagram. Let me try if I can be able to draw it somewhere. So our block diagram can be kind of, okay, let me try to do it even here. It's gonna be like this one. We have this summing points, then we have this, and we have this. Okay, so this one is G3 plus G2 plus G2, and this one is G1 times G4. Okay, so in between here we have this feedback H1, H1 here. Then this one is going to the feedback there. Okay, this is there is plus there and there is plus there. So this is what we have. Then we have the second. Sorry, we have the second. I think we have the second feedback, which is this one. Let me go back and see what was it. H2. So this one gonna be H2. H2. Okay, H2 going to this. There's another summing point somewhere there. Then connect this. Okay, if you can see this one, you will know that. So now we're having this one. This block diagram of G1, G4 is not in series. It's not in cascade of this one because here there is another feedback. So there is another takeoff point which is giving us as a feedback. So these are not, we cannot multiply them. So we need first to remove this feedback. Then the block diagram that can have for these two can be in cascades with this one. So that's why they show this feedback here. After they do the feedback, they're gonna get this one. So we're gonna get this one after the feedback. Then we are going to put it at this place here. So that's what we have, this one. And then in that case, now we have this one and that one, they become now in a series. So we can do this one times this one. And if they say, let's find the canonical form. So after just doing this cascade operation, we can stop by there and say, okay, we have got our canonical form where when we have one transfer function in a feed forward and another one in a feedback. So this is what we have. This is what we can call a canonical form. But if they ask you to find the equivalent transfer function, still you can also do this feedback too, and you're gonna get the answer to that one. So there is another example here, which is also quite interesting. Are you guys there?
No.
Yes.
Why do you say no, but you are there?
No.
Usisi, is it difficult?
Yes.
No, it's not difficult. Now we will do more example in class. I think I want us to finish with all the theory, and probably this is we have done with this chapter, and then Wednesday we'll do the last chapter, and from Monday we're gonna be doing tutorial. Okay. So now there is another exam. They say we need to simplify the block diagram. So how can we simplify the block diagram? So now we need to know exactly what to do, because here there is no way to find the cascade. This one is not cascade. So this one also is not parallel. So there is no parallel, there is no cascades. So there is even no, we cannot even say that there is a straight feedback that we can do and say let's use this feedback side by this feedback. So in this case, we are required to now to move the summing point. So we can remember there is a two-way of moving the summing point. Remember here, we say when we want to move the summing points, when the summing point, we can move them, the summing point ahead, or we can move them, the summing point, oh, that is the takeoff point. So if we want to move this one ahead, we have to multiply by 1 over g. So we move in the other way. So let's go back now here. Let's say we want to move one of the summing points here ahead in order to get, so this other transfer function must be divided by this one by j. That's why we are moving this one here. So we can move this one too. We move it here, then we divide this by j, and that allows us now to have this one as cascades. So because we have these cascades, it's now easy for us to solve this cascade. Gonna be G1 times G2. Then after to solve this one, we're gonna have now a feedback on this tree. So when we have the feedback, we might be able also to eliminate this these summing points. So that's gonna allow us to have these two. They're gonna be also in series with the feedback transfer function that we're gonna go for this one, and that's gonna allow also us to find this one. Let's go slowly. So you can see now here, because they have jumped some step. They got first this one G1 times G2. Then after they do here, so after now they can do the feedback. So this is now the feedback. Once they do the feedback, they're gonna get this, and this gonna allow to have these two as cascade. Then we're gonna get something like this. Then this one also will be a feedback. We can solve the feedback. We got this this system here. Then after that, we can go back and we have a unit feedback. If they wanted to get in form of unit feedback, we can stop here, because they say we have to simplify it. So it's just to find the final transfer function. That's why we also simplify this. We eliminate also this last feedback, the unit feedback. So thank you very much. I think we have done with section. This is section 4. We have done with this section 4. Then next week we'll do section 5. Then from the other Monday we'll be doing tutorials. But I will see if possible we can do some tutorial also online. I'll just maybe try to write them, so we're gonna be able to do more tutorials. So we cannot be resting when we have online class. Thank you very much. Is there any question?
Sir,
Yes.
where can I get this slide?
The slide. Okay.
This slide.
Are you in the group?
No, I'm not in the group.
Yeah. But you have my number, right?
Yeah, I do have.
Send me a message saying that you are the one who was for the slides. But I'm sending them now in the group. Then I also put them in. I'll also put them online on the Microsoft team. But I'll try to sort out. I don't know why I'm still having problem with the blackboard. So I will see how I can do during the weekend if I can upload the video also on Blackboard. I think I'm sending to you. Send me just a message. I'm going to send to you this. I think. Thank you very much.
Okay.
Is there any other question?
Okay, thank you, sir.
Yes, sir.
Yes.
I heard something about the assignment, which is June, Monday.
Yeah, I'll confirm with you during the weekend. I can send you some questions that you can solve. But I would like to do it online if I can do. So we're gonna be solving to learn, but I'll confirm with you on the weekend. But that's gonna be just simple application. Then you can solve and you will bring it on Monday.
That is simple to hear.
Why are you crying, sis? Usisi, why are you crying? Okay, guys.
There's nothing simple.
On Monday, sir, are we having breaks?
Yes, we're having break at the first one will be Group C. Group C 9:50 to 10:45, and then the second one will be at 1 o'clock. Group A, A day. The second one will be at 2:30. Group B. Then the last one will be at 7 o'clock. That will be group the evening group, the two evening groups, all the evening groups. Thank you.
Monday.
Any other question?
So the breaks are Monday only.
Yeah, only on Monday. Because we will have class on Wednesday and Thursday. Maybe if we finish